Okay, so last time we talked about, we defined representation, representation of groups. So what a representation is. So I'll just recall. Recall that if G is a finite group and V is a finite dimensional vector, so I mean, the definition you can do it for arbitrary groups and arbitrary dimensional vector space. It need not be finite, but we'll study only representation of finite groups in this course, and all our representation will be finite dimensional. Yeah. Then a representation of G is a group homomorphism from row from G to GLB. Yeah. So that is a representation. So in this case, V is said to be a so this vector space V is called a representation of G. Yeah. So sometimes this row is sort of assumed. So so equivalently, you think of V, a vector space together with a G action. Yeah. And the action is not some arbitrary bijection, doesn't give you some arbitrary bijection of V, but a linear map. Yeah, so that is what a representation is. So another way of thinking of it is it's a vector space together with a G action on it. Yeah, and this G action has this property that G dot V1 plus AV2 is G dot V1 plus AG and G dot V2. That means G dot is a linear map. So G dot is same as rho G in the previous definition, yeah. And we want rho G to be a linear map. So similarly, so that will give us this condition. Okay. So and then we saw some examples of representation. So one example was so if you want to give a one-dimensional representation of vector of a group, and that's same as giving a map row from G to GL of a one-dimensional vector space, which is just K cross, where K is a field. And so giving a one-dimensional representation of G is equivalent to giving a group homomorphism, row from G to K cross. Yeah. So every one-dimensional representation looks like this. Right, and one particular one is when you take the trivial representation, when every element of G goes to the multiplicative identities of K cross, which is 1. Yeah. So one, the element 1 of the field, base field. So that, which means that in terms of action, it means that G acts trivially on this one-dimensional vector space. Okay, so here somehow, if you write it this way, then the vector space is missing because you have identified GL one-dimensional vector space as K cross. So you can think of here the vector space as K, yeah. So, and the action, so maybe I'll write it here, yeah. So here, if you want to think in terms of vector spaces and action, here take V to be K, and then the action. And then K cross you can identify with GL1 of K. Yeah. So how do you think of it as? How does K cross act on? It's just scalar multiplication. Yeah. So just the multiplication. So then G dot A is just rho G, which is an element of K cross and hence of K, and you just multiply. Yeah. So it's just multiplication, ordinary multiplication in the field. Okay. So that is how one-dimensional representation looks like. And then we also saw regular representation, definition of regular representation. We saw permutation representation. So if you have a group acting on some set, then you can always make that set into a vector space, and G will act on it linearly. So you think of elements of that set as a basis of your vector space, and then it acts via permutation. So, and the special case is permutation representation. This regular representation, which is basically KG. Yeah, your vector space is K, the group ring KG. So it's a special case of permutation representation where X is G itself, and the action is, let's say, left multiplication. Yeah. And so I don't know if I said this. Did I define? No, maybe I didn't define this. Yeah. So let rho from, so when you are given two representations, rho and rho prime, on maybe two different vector spaces, V and V prime, then you can define a map between two representation. Yeah. Homomorphism of representation. So they are not so you'll see that there are not too many non-trivial maps between representations, yeah, in some sense. So I will make this more precise. So there is so if you have some so there is something called irreducible representation. So if you have something called irreducible representation, then there are not too many maps from that representation to itself. Yeah, so that they are just scalar multiplication, scalar maps. And you'll see that if you have two distinct irreducible representation, then there are no maps between them. So it's not, that's why it's not, in some sense, it's a somewhat trivial notion. Yeah. So a linear map tau from V to V prime is said to be G, is also sometimes called G equivariant. Yeah? So it's called G equivariant if or a homomorphism of representation if this tau commutes with this G action on V and V prime respectively. So what it means is that rho G, so rho G acts on V. So rho G applied to an element of V will send it to V, and then you apply tau, you get into V prime. That's same as first applying tau to the vector and then applying rho prime G. Yeah. So that is what this a map, a G equivariant map or a homomorphism of representation is. So equivalently, what you can say is, yeah, this is what I said. Yeah, tau G dot V is G dot tau V for all G in G and V in V. And if tau is an isomorphism, then rho and rho prime are said to be isomorphic representation, or sometimes also similar representation. Similar because if you think in terms of matrices, then it leads to similar matrices. Yeah. So for instance, if you, yeah, so maybe I'll say a little bit here. So for instance, if you fix a basis of V and V prime, then tau will be given by a non-singular matrix, yeah. Which so if you fix a basis of V and the basis of V prime, then tau will be given by a non-singular matrix. And then this relation rho G also, you can think of it as a matrix with respect to that basis. Rho G is an automorphism of V, and hence it will give you, and if you fix a basis, it will give you a non-singular matrix. So this relation, so this one translates to, in terms of basis, it translates, you can see this gives you rho G is tau inverse rho prime G composed tau. Yeah. So tau will correspond to a matrix, and from V to V prime, and then the change of basis matrix from V prime to V will be the inverse of that. So you will get that rho G and rho prime G, they are conjugate by this this matrix. So this matrix. So not just rho G and rho prime G are similar. The change of basis matrix is sort of the same. Yeah, so the same tau works for all G. Okay, so that's what two isomorphic representations are. So they are basically the same representation. You're just sort of given it a different name. So if you identify V and V prime via this this map tau, then this rho changes by conjugation by some non-singular matrix. Okay. Any questions? So I hope this is clear. This you must have seen in linear algebra. So I'm not trying to do it. Trying to overdo things here. Okay. Any questions? Okay. Okay. So sorry. Yeah. So let V be a representation of a group G. So this we defined last time. So sub-representation. Yeah. So a subspace W of V is called a sub-representation. Sub-representation of V if this condition holds. So W should be invariant under the action of G. Yeah. So not invariant, stable under the action of G. So W as a subspace is sent to itself under every element G in G. Yeah. So rho G of W is in W for all W in W. So rewriting this, you say the rho G of W is contained in W. Okay. Yeah. Okay. So I suppose this is clear. Yeah. So it's written with vanishing ink, so it vanished. Okay. So so if you are given action row of you are given a representation row, so that induces this G. That means you are given this homomorphism Z to GLP. Yeah, and of course, if you take a sub-representation, then you get this map G to GLW as well. And how does this map go? So it's just the restriction. Yeah. So rho G is a rho G W, rho sub W of G is some element of GLW. Yeah. And what do? You just consider rho G and restrict it to W. So if you want to write in terms of matrices, it looks somewhat clumsy. Yeah, because you'll have to worry about what basis you have started with. So of course, if you start with a basis of W and then extend it to V, then it will be nice. Then you just have to take this. Then it will be a block. If W is a sub-diagonal sub-representation, then it will be a block matrices because elements of W map to W. Yeah. So you can take the diagonal part. Yeah. Or the top diagonal part, so to speak. But if you do it abstractly, then writing the formulas are straightforward. It's just a restriction of the map on V to W. Okay. Is this okay? Yeah. So we saw some example as well. So we saw that in the regular representation, we saw an example of a sub-representation. So basically, you take the sum of all group elements. Yeah, so we saw that that's a trivial sub-representation of the regular representation. So we will see one more example because maybe, yeah. So, but before that, if you consider the inclusion map W to V, where W is a sub-representation, then of course the inclusion map is G equivariant. Yeah, it's sort of I don't know. It's a tautology, right? Because so maybe write it properly. Since so, what do we want? We want to say that I is a homomorphism of representation of G equivariant. So to check that, what do we have to check? We have to check that I G dot W is G dot IW. Yeah, but I is the inclusion map. So this is saying G dot W is G dot W. Yeah, with as I is inclusion. Yeah, so this is, and that's why I said it's a tautology. So if you include a sub-representation in the ambient representation, it's trivially a G equivariant. Okay. So now if you consider, this was the regular representation, and yeah, this is what we talked about. So W is a sub-representation, yeah, and it's a trivial representation, right? So one way to, so another way to give a equivariant map from a trivial. So let's say, so you know there is a one way to write the trivial map is maybe W prime is the base field K, and rho and G dot K is sorry. So. Yeah, W prime is K, and G dot A is A for all A in K and G in G. So this is the trivial representation. Yeah. So if you want to give a G equivariant map from W prime to V, so how do you give a G equivariant map from W prime to V? So maybe tau, yeah. So tau from W prime to V. So what will be the equivariant G equivariant map from W prime to V? So W prime is same as K, yeah. So where will element of K go to? In V, V is Kg, yeah. This is Kg.
A times summation G.
Yeah, so you can send it to A times summation G. Yeah, so this is of course tau is of course a linear map, yeah, because you know, just giving a map from the field to this and defining it. So it's a linear map, and it is equivariant. So G dot A is G dot A is A, and here also G dot on this side is that thing itself. Yeah. So you can check that this is tau is an equivariant map, is G equivariant. Okay. So that's so that is giving one. So we found one sub-representation of this regular representation. So I wanted to do one more example. So on Kg, yeah. So you take G to be Z mod NZ, yeah. So of course, one sub-representation we know is you just take this W generated by sums of all the elements of G and G in Kg. Yeah. So that's that's a one-dimensional representation and a sub-representation of KG. But there are there are some other non-trivial one-dimensional representation of G. Yeah. So giving a one-dimensional representation is just giving a map G from G to C star. So what you can do is send 1 bar to e power 2 pi I over n. It has to go. So remember, we know that the image has to be in C star. Yeah. In the unit, it has to be roots of unity. Yeah. And here, if G is the cyclic group of order G mod and Z, one has to go to one of the nth root of unity. So maybe we will take this map. Yeah. So there are only so many representation, one-dimensional representation of this Z mod and Z. Yeah, it all determines they are all determined by where one bar goes, and there are only so many. There are n possibilities. Yeah. So if it goes to the identity element, say if it goes to 1, then it's the trivial representation. If you send it to this guy, then you get one representation, and you can send it to powers of this. Yeah? So that n possibilities. So let's consider this. So this is a representation of one-dimensional representation of G, and it's a non-trivial representation. Yeah. So this is a non-trivial representation, and so last time I also told you, though we haven't proved, that every representation sort of appears here. Yes, every what is called a irreducible representation will appear here. So all one-dimensional, so we'll define irreducible representation today, hopefully. So one-dimensional representations are trivially irreducible. You can't make it smaller anyway. Yeah. So this should also appear in KG. So so we should figure out how does this appear. Yeah. So now I'll tell you how does this appear. Yeah. So that means there should be a G equivalent map from this representation, the representation row to KG. Yeah. So the way to do it is pick out the right one-dimensional space. So if you think about it, you take this vector V to be e power 2 pi I L over n times L bar. Yeah. So this is how a typical element of KG looks like. C Z mod and Z looks like. So here now K is C. Yeah. So K equals C. So this is how a typical element of C, Z mod and Z looks like. Yeah. So some complex numbers times the group element. Okay, so V is this. Now, if you think about it, what is M bar dot V? So the action is, so it turns out to be this. So let me, okay, maybe I should do this computation. Yeah. So let me erase this. So what is M bar dot V? So if you, by definition, it doesn't do anything to the coefficients. Yeah. So L equals 0 to n minus 1, e power 2 pi I L over n dot M bar times L bar. Yeah. But here the group operation is addition. Yeah. In Z mod and Z. So this is M bar plus L bar. Yeah. So this is what this is how it works. Yeah. So and this how do I? So but I want to rewrite this in terms of V. Yeah. So what I'll do is I'll just multiply this vector. So this is so this I can think of it as summation L equals 0 to n minus 1 e power 2 pi I L over n. But if I want to write, so if I want to write it m plus L over n, then it will be a more reasonable thing to do. Yeah. So I'll write it as m plus L over n. So L plus m over n. Yeah, but I have multiplied by, so what I've done is multiplied by e power 2 pi L, 2 pi m over n. So I should divide by that. Yeah, so e power minus 2 pi I m. Yeah, so I had something wrong in here. So good that I erased it. Yeah, times m bar plus L bar. Yeah, so this is how you can rewrite it. Yeah. But now the point is this does not depend, this factor, the other factor doesn't depend on L, so we can pull that out. Yeah, so this is just e power minus 2 pi I m over n. So m is some representative, yeah, it doesn't matter in the integers whose image is m bar times v. Yeah, so instead of running L equals 0 to n minus 1 is same as running m plus L equals 0 to n minus 1. Is this clear? So what we get is that m bar dot v is some scalar multiple of v. Yeah, right. So we have figured out, so if you consider the subspace generated by, so if you take W to be the subspace generated by V, then it is a sub-representation. So W is a sub-representation of W is a sub-representation of W is a sub-representation of C Z mod NZ, and it's of course one dimensional. And what do, yeah, so we want to give an equivariant map. Yeah, so you want to give an equivariant map from rho to kg. So rho rho is given by this. So the vector underlying vector space for rho, remember, is the base field C. Yeah, so I'll give you tau from C. So if you want to give a map from tau from C to the sky, kg, or C Z mod NZ. So what should be the equivariant map? So where should one go to? So it should pick out this subspace W. Yeah. So you can send it to, yeah, you can send it to V, this vector. And once you know where one goes, you know where any other element of C has to go, because the linear map is G equivalent, is Z mod and C equivalent. Okay. So of course you can send it to any scalar multiple of V as well. It need not just go to, so you can check that even if you send it to some 2 times V, it's still okay. Any questions?
So if you have Z mod NZ and N is odd, then the sum of the group elements will be 0. So how does the regular representation behave? Like how do we find a one-dimensional sub-representation then? Because we can no longer take span of the sum.
Yeah, but we are taking, so we are not really, so these are linearly independent, so these are symbols, G, okay? So you can't do cancellation. So maybe so C is at N. So maybe maybe there's some misconception. Yeah. So the elements are of the form A times 0 bar plus A0 times 0 bar, A1 times 1 bar plus AN times AN minus 1 times N bar. Okay. So this is how a typical element of Z mod NZ looks like. Yeah. So even if you put all of them to be 1, that doesn't mean that you can add them. Yeah.
Oh,
so
okay.
it's a vector space of dimension n, and the second terms you should think of them as symbols. Yeah. So it's unfortunate notation because here the vector space sum is also plus, and the group operation is also plus. Yeah.
Yeah,
But
okay.
yeah, maybe I should have done the multiplicative notation for the group, mu n or something. Yeah. Then maybe less confusion. But this plus is vector space. Yeah, these additions are in vector space. So that's why, people say you should be very careful about notations. So we do simplify, but you should, from context, it should be clear. Yeah. And then the group operation is also plus, but maybe, yeah. So then maybe just to complete the picture, M bar, yeah, so maybe this one should put this plus here. So this is the group operation plus. Yeah. Plus in Z mod and Z. Okay. So in the group operation. So M bar dot so maybe this is the action. So just M bar. So yeah, even the action, maybe it's a good idea to distinguish it. N bar is, so if Z mod NZ is a group with the group operation this, let's say, then this is M bar, I don't know, A0 M bar plus 0 bar. Yeah. So it's going to be M bar itself, because M bar plus 0 bar is 0 bar. M bar, so next term will be A1 M bar plus 1 bar, which is M plus 1 bar. Yeah. But this plus and this plus are different. Yeah. So that's what is leading to the confusion, I suppose. Sorry, this should be N minus 1 bar. Yeah, once you write examples, things go crazy. Okay. Yeah. So is this clear now?
Yeah.
Yeah. Okay, good. So so it's just yeah, notational confusion. Any other questions? Maybe the notation may have created more confusion. But it's a good question. Yeah. So because this could have led to some confusion. Okay, good. So you saw another example of a sub-representation and equivariant representation. So in fact, as I said, every irreducible representation we will see appears in K. We will see a proof of it as well. But first we have to define what a irreducible. So maybe before going to the main proposition today, let me just define irreducible representation. And then we'll go to that proposition. So I was planning to do that proposition first. Definition. Let V be an irreducible V be a representation. V be a God. Yeah, representation of a group G. It is said to be irreducible. I don't know what's this. Yeah, this is terrible. Said to be irreducible if it does not have any non-trivial subrepresentation. Non-trivial representation. It doesn't have any non-trivial representation. So what are so there are two trivial representation, yeah, the two trivial non-trivial sub-representation I meant. Okay, so sub-representation, non-trivial sub-representation. So there are two trivial sub-representation. One is this zero subspace, yeah. You can take zero subspace, and the other one is the whole space. So apart from this, there shouldn't be any other sub-representation. Then you say that this representation is irreducible. Okay. So so of course, so that tells you that. So example. Every one-dimensional representation is irreducible. Yeah, because of course that's trivially true. Yeah, you can't even have a non-trivial subspace. Yeah. So we will see that using the next proposition that if you are given any representation, then you can decompose it as a direct sum of irreducible representation. If you're so in this case the field so this but this statement holds for complex representation, or what you need is characteristic zero. Yeah, so this is where characteristic zero is very crucial. So so that's why representations become so if you are trying to study representations which are not characteristic zero representation, they are very difficult. Yeah, so there is a whole area called modular representation, which is so if you want to so what you need is the order of the group should be invertible in the field over which you are trying to do the representation. But if that doesn't happen, then what you get is called modular representation, and very little is known in about modular representation. Is what
so it's enough if the prime characteristic just doesn't divide mod G, right? The order of the group, not necessarily zero.
Yeah, then also the same proof, as you will see, will show that you can always decompose that any representation of G in direct sum of irreducible. But if the order of G divides the characteristic of the base field, then you can't. Okay. Any other questions or comments? Who was this? Who made this? Who asked this?
Shahbaz.
Sabas. Okay. Yeah. I'm just trying to identify at least voices, if not faces. Okay. So let's get to the proposition, which I was trying to allude to. Yeah. Is this okay? So I don't know if the left-hand side is visible. I hope so. A bit of left-hand side is also visible, and the right-hand side is completely visible. Is this okay?
Yes, sir.
Yeah. Okay, so the point is, so if you so the next theorem says that if you have a representation and you have a sub-representation, then you can decompose it as you can find a complementary representation. Yeah, so there's some typo here. So let me just first fix this. Yeah. Okay. So let rho be a representation of G and W be a sub-representation of G. Then the theorem says that there exists W0 in V, a sub-representation of G, such that V you can write it as W plus W0. W0. Yeah, so that should be subscript. So let me. W0. Okay. Good. So W0 here is a complement of W in V, and that means they together, W together with W0 is whole of V, and they intersect only in 0. And W0 should be a sub-representation, which is same as saying that is stable under G action. Yeah. So note that once you have this, then of course it's clear that you can sort of decompose. Yeah. So we'll see that as a corollary of this theorem. So this is the main thing, and then as a corollary, you get that every representation you can write it as the sum of this one. So how do you cook up W? So as you know, W is some complementary guy. Yeah. So what we do is take some projection onto W. Yeah. So you start with a projection map P from V to W. So what is a projection map? So on the subspace W, it should be identity, and everything outside W. And the image should be W. Yeah. So anything. A way to construct a projection map is you start with a basis of W and then extend it to a whole of V. Yeah. And then those which are not in W, you send them to 0. And those which are in W, you assign identity map. Yeah. So that will give you a projection map. So you start with a projection map of W. So which means Px is X for all X in W, and Y is the image of P is in W, and P is linear. So of course, this will have a kernel, yeah, because the kernel plus so the image is whole of W because it's identity on W. So the kernel will have a dimension same as dimension of V minus dimension of W. Yeah, so let's call W prime to be kernel of P. So we know that V is a direct sum of W prime plus W. Yeah, because you sort of have a splitting. Yeah, so we know this even for modules. When you have a splitting, you can write the middle guy as the direct sum of the right-hand side guy and the left-hand side. So in modules, this is non-trivial, but in having a splitting, but in vector spaces, you can always find a splitting. Yeah. So V, you can write it as W prime plus W. So getting this W prime is not, but there is no reason for W prime to be stable, right? So finding a complementary subspace is not a problem. That's always there. But you want the complementary subspace to be stable under G action. Yeah. So the way, so now W prime need not be stable under G action. So one way to do it is there is this averaging technique, which we'll do. Yeah. So you consider this different projection map. Yeah. So so we'll see that this is in fact a projection map. So what you do is conjugate this P, this linear map P by rho G. Yeah. So you define this component. So rho G inverse is a map from V to itself, and then P will send it to W, and then you apply rho G. Since W is a sub-representation, that gives you an element in W again. Yeah. So and then you divide by 1 over G. Yeah. So you have to divide by 1 over order of G to make sure that it's a projection. So let's see why P0 is a projection. Yeah. So so this is a projection because if you take, so first we have to show that the image of P0 is actually in V. Yeah, it is in W. So first of all, the map makes sense. Yeah. So because rho G inverse takes V to V, and so P is also, you can think of it as a map from V to V itself. Yeah, just that the image happens to be in W. Yeah, so you include it in V. Then so these are composition of 3 maps from V to V. So I guess projection, people also think of it as a map from V to itself, such that the image is W. Yeah. So there are many ways. Yeah. So maybe projection means it is in V. Yeah. So yeah, so maybe I just want to keep it this way. Okay, good. So so P0 makes sense. It's an endomorphism of the vector space. Now we want to check that the image is W, and we also want to check that its identity on W. So you take any element of V, then of course P0 rho G inverse X is in W because the image of P is in W. Yeah. So and W is a sub-representation, tells you that this rho G composed P composed rho G inverse, this guy applied to X is also in W because W goes to W under this rho G action. Yeah. So that tells you that that you start with any element, and this particular term will send it to W. So, and of course, P0 is sums of this. So sums of elements in W is again going to be in W, and because it's a subspace. And then you multiply by 1 over order of G, so it still lands in W. So this is where so for defining P0, we need 1 over G to make sense. 1 over order of G to make sense, yeah. So we see that image of P0 is indeed W. And then we want to check that its identity on W. So you just check that. So for X in W, what does each of these terms do? It sends it to X itself. Yeah. So so it sends it to X itself because you know, rho G inverse of X will be some guy, and but P is identity, but it's going to be some guy in W. If you start with an element of W, because W is a sub-representation. Yeah? And P is identity on W, so you get this. And so here we are using non-vanishing. W is a sub-representation. Yeah. Representation. Okay, and then of course the group action is tells you that rho G inverse of X is just X. Okay, so P0 is a projection map. And now if you look at kernel of W0, so this averaging has the advantage that this kernel will be a sub-representation. Yeah. So now W0 is a complementary subspace of W, but it has also the advantage that it's a sub-representation. So let's just check that. Yeah. So this is just trivial, yeah, because if you so note that if you conjugate P0 by rho G, you look at this formula. Yeah. So you look at this formula, you can conjugate it P0 by rho G. Yeah. So rho Z0, let's say, for some Z0 in G. Then if you conjugate it by rho Z0, it becomes rho G0, rho G P, rho G0, rho G inverse, rho G0 inverse. Yeah. And then rho is a homomorphism. So what you get is, yeah. So do you want me to do this? Maybe, okay, maybe I'll just write this down. Yeah. So this is rho G inverse. So maybe 1 over size of G summation. So maybe I'll do it for, okay, here I'll put some H, or let's do this for G0. Yeah, for all G0 in G. So that it works the way I said. Rho Z, what was the formula? Rho Z, yeah. Yeah, I don't know. It's, okay, it doesn't matter. P rho G inverse rho Z0. Yeah, so I conjugated by this way, but so it doesn't matter. So this is, so you have to take sum over this. So I'll push this inside, yeah, and pull out the summation Z. So this is same as 1 over summation G, 1 over order G, sum G in G, and rho. So rho Z0 inverse G is same as rho of Z0 inverse G, P, rho of G inverse G0. Yeah. So you sum over all G in G, this is same as G0. Yeah, because Z0 is a fixed guy in G. And the inverse of G0 inverse G is G inverse G0. Okay. So you get that this is same as P0. Okay, so hence you get that. So if you write the statement alternatively, meaning move this the other side, you get that rho G P0 is P0 rho G. Yeah. Which implies that if you start with some, so this is, so what it means is this, yeah, so P0 is yeah, so it's a equivariant, G equivariant maps from W0 in some sense, P0 inverse, not P0 inverse. Okay, whatever. So I want to say that W0 is a sub-invariant, so a sub representation. So you start with X in W0, then this identity tells you that P0 rho G X is same as rho G P0 X, but P0 X is it's a projection, right? P0, so it's same as rho G X. Yeah. So what it is, so what it says is that P0 maps rho Gx to rho Gx, yeah? So that tells you that rho Gx must be in W0. Yeah? So since P0 is a projection, yeah. So projection. No, sorry. So I messed it up. Yeah. So it's not. It's 0, right? So W0 is the kernel of rho 0. So I mean, it is the final conclusion is true, but so you start with x in W0 and you apply rho g to it. So you want to say that it still lands in W0. Yeah? So so P0 of rho g x is rho g of P0 x, but P0 of x is what did I do? Yeah, so W0 is kernel of P0, yeah? W0 is kernel of P0. So P0x is 0 and rho g is linear, so this is 0. Yeah, so this is okay. So I had something wrong with it. So this implies rho g of x is in W0, which is kernel of P0. Okay. Okay, so I replaced W0 by W in my head. Okay, so that tells you that W0 is a sub-representation. You start with anything in W0, you apply a rho g to it for all G. So this formula works for all G. Okay, any questions? Yeah, so that completes the proof. We wanted to get a complementary dimensional, complementary subspace, which is a sub-representation. Yeah, and that's what we did. Yeah. So let me stop the recording. It's also time.